Today we're going to talk about complex splitting because last lecture was a flaming hot mess, and it looked like everyone went into it looking kind of confident. They were like, "Yeah," and then he started talking about stuff, and I saw everyone's face like. So hopefully we're going to fix that a little bit. Before we do that, I kind of wanted to summarize what we've done in past SI sessions with an exam-like practice problem. And I also want to point out something that I don't know if I said in SI or tutoring, but we're going to talk about it. So where is the heteroatom region? Okay, cool. So a heteroatom is anything that's not a carbon or a hydrogen. The heteroatom region is 3 to 5 ppm. And within that region, we can get more specific. So let's say this is 3, this is 5. And let's say right here is 4. So the heteroatom region for the purposes of this class is going to contain nitrogen, oxygen, and fluorine. I really had to think about it. Okay. So out of these three, which one is the least electronegative? Nitrogen. Cool. So the less electronegative it is, the lower the number it will have. So nitrogen is about at a 3. Oxygen is at a 4. Fluorine is at a 5. And so basically what this means is if he gives you something like this, and he asks you for the chemical shift, it's going to be right around 4. If he gives you something like this, for example, that's not only a nitrogen, but it's 1 carbon away from the nitrogen. So it's going to be on this low end. Whereas if he gave you something like this, that would go like around 3, but a little bit higher than 3, you know? And then if he gave you like FH, that'll be right at this 5 region. So when he gives you questions like this one on the board, that's how he wants you to differentiate between like 4.5, 3.4, and 5.2. Make sense so far? All right, awesome. So I will leave this up for 2 seconds, and then I'm going to erase it. So let me know when I'm good to erase. We haven't done it yet. Yeah. Okay. Can I erase? All right. So for this question in particular, it is basically asking you for these hydrogens, and it wants the chemical shift and the coupling. So what's another word for coupling? Splitting. Alrighty. And chemical shift is what? What does chemical shift tell us, I should say? How shielded versus how de-shielded. Awesome. So when we're talking about this example, the first thing I want you guys to tell me is what region is it going to be in? Well, even more general than that. Yes, so the reason it's in the heteroatom region is because it's connected to a carbon, and that carbon is connected to an oxygen. So we're going to say heteroatom region. And we talked a little bit more about like the specifics of that region, right? So as Luke said, oxygen is around a 4, right? So if we're on a carbon, then an oxygen, is it going to be higher than 4 or lower than 4? Yes, I'll repeat the question. So if something is directly attached to an oxygen, it's going to be like a 4, right? Because it's de-shielded. If it's attached to a carbon that's attached to an oxygen, is it going to be more de-shielded or is it going to be more shielded? More shielded, so it's lower. Exactly. So we're going to say this is like lower. Whatever, I'm not going to say that. Yeah, I'm going to say around 3.4. That looks good to me. Which two options could we completely get rid of before we thought about anything? And I'll say, hold on. A, B, E. Two of them we can get rid of just by knowing what the heteroatom region is. C and D, because 1.0 and or 1.1 and 2.1 are not in that region, right? So we're down to those three. Now that we have that, we can pretty much say that it's E, right? But let's double check. Does this purple hydrogen have any neighbors? Let's look. So 1, 2, 3, no neighbors. 1, 2, depending on what day, Dr. West and how he feels. 3, no neighbors. So it would be a singlet, right? But that makes you run into a problem, right? Because now you have those conflicting things. So test taking skills. What would you guys pick? A, because why? Because you know for sure it's a singlet, cool. And is 4.5 close enough to the range you expected? Yes, okay. So this is one of the like more tricky ones that he'll give you. Yes. It would be. This is one of those tricky ones because it could be anywhere between 3.5 and 4.5. But he will give you a number that will kind of throw you off. So you know that if this was a perfect world, that would be around a 3.4, 3.5, but it could be anywhere in that. And your name is Eric, right? Okay, so if you're comparing OH versus this, oxygen is super electronegative, so it's pulling this electron density super far away from the hydrogen, right? This one has this lovely carbon in between, so this is still pulling all that density, but because of the carbon, the hydrogen gets a little bit more of that shield because it's further away. And let's do all the way up here. Don't look. So this one, it's almost exactly the same thing, but this is more of the straightforward one. So, what is the multiplicity of those hydrogens? Singlets, cool. So knowing that, which one of these answers can we get rid of? B and C. Cool. So now we do have to think about the ppm range, whatever. Which one can we automatically get rid of? D. Why is that? Exactly. So we want the heteroatom region. Okay, cool. So now this is a hydrogen attached to a carbon that's attached to an oxygen. Same exact thing we were talking about last time. But now you have to pick between 4.5 and 3.4. 3.4, because that is the better answer if the singlet thing matches up. So that's why I kind of explained it the way I did. Does that make sense? Yes. Because if it's, so oxygen is about at a 4, right, on the scale. If it's directly attached to the oxygen, it'll be like right at a 4. If it's a little bit further away from the atom, it's going to be more shielded, so it'll be like a smaller number. Repeat that? Yes. Compared to what? Yeah, you can think of it that way. Okay. Any questions about this? So the hydrogen is attached to a carbon, and that carbon is attached to an oxygen, right? That oxygen is super electronegative. It's stealing all of the electrons. So if that hydrogen is further away, it's going to be able to keep its shield a little bit more because it has more distance, right? Whereas if it's directly attached, it's going to steal all its electron density, so it's going to be super deshielded, which would be a higher number. Okay. I'm so glad you guys are participating and asking questions and having me repeat things. I love it. I love in-person. Oh, I lost it. Love it mostly. Okay, so today we're going to do complex splitting and have enough time. And after what you all went through in lecture, I want you to please answer this with a new, fresh state of mind. You've never seen this before. Pretend that didn't happen. Nobody's traumatized. Don't freak out until I'm done. Promise? Okay. So, we're going to do there we go. This is the molecule I'm giving you, right? And before we even start with complex splitting, we're going to talk about what the heck that is and why it's different than normal splitting. So last time we did normal splitting and we did this tree diagram and we found out it wasn't as complicated as, you know, it could be. But again, you guys don't ever have to reproduce this. It's just good for theory. So the whole basis of these tree diagrams has to do with J values. Does anyone remember what I said about J values? Yes. Yes, exactly. So those are synonymous with one another. Exactly. What else do you guys remember? Perfect. Okay. So it is right up here. So I'll move it up in case you didn't have that. So J value is essentially just like the value by which two neighbors are going to split one another. And like we talked about before, what that means, right? And the value it's splitting it by is just the distance between, right? J value, right? He went on about how to tell if J values are different or the same. For the purposes of this class, if the two hydrogens have the same hybridization, they're the same J value. They have a different hybridization, they're different. And I will show you what I mean. Okay? All right. This carbon right here, what's the hybridization? This one. sp3. Does anyone not remember at all hybridizations from Orgo 1? Yes, okay, cool. So all you need to know for Orgo 2 is sp3 equals single bonds, sp2 equals double bonds, and sp equals triple bonds. Yes, sp2. Yes. Exactly. Everything they do in Orgo is just to mess with students. Yes. The other thing I want you guys to write down for future reference: triple bonds are linear. Have to be linear. sp2 is planar. That's it for now. Not that big of a deal. We're going to use as few chemistry words as we can. So based off of what yes. Exactly. It's all composed of single bonds. And as I drew in there, it's pretty. So we know that it can't be sp2 or sp3. I mean, sp2 or sp because we just said they're linear and planar. right? So all that being said, what's the hybridization of this carbon over here? Also sp3, because it's all 3D looking and it's all single bonds. So that being said, these two hydrogens have the same hybridization, so they have the same J value. So this is normal, regular old splitting, and that's why we use the N+1 rule. Let's see an example where they're not the same. Wow, how convenient. I have one for you. We started with red, all right. I don't know why these lines are so thick today. Alrighty, so we're gonna go left to right. This carbon, what's the hybridization? 3. This carbon. sp2, this carbon. sp2 because it's also connected to this double bond, right? So both sides are sp2. We don't care about the rest of it. So the reason this is important is because this hydrogen couples with 1, 2, 3, all of these, 1, 2, 3, all of these. And so since this hybridization is different than this one, that means this J value and this J value are different. So I'll say J1, 2. I'm going to say J1 does not equal J2. And the reason I'm phrasing it like that is because he'll say something about it. All right. So I am going to make up J values for the purposes of making a tree for you guys. So these are not the exact J values. I'm just making them up. Okay. So we are going to say that J2 equals 10 hertz. And we're going to say that J1 equals 5 hertz. What's the only J value I expect you guys to know already? 7 hertz, because that is what? Normal, average, most common, yes, but what kind of hydrogens? How are they related? That might be a weird way to say it, but adjacent hydrogens, right? And those are called vicinal hydrogens. So regular old hydrogens that are on adjacent carbons are 7, correct. All right, so this looks like a hot mess, but let's fix it up. So we are doing the splitting for the red hydrogen. So I chose that. That's what we're doing for no reason other than because I want to, okay? So we have that red hydrogen. It's just a signal, right? Just hanging out, being a signal. How many neighbors does it have? 4. So can we do 4 plus 1 and say it's a quartet? No, why not? Or it would be a quintet, you're right. But other than that, why not? Because the hybridization is different. So, oh no, if we can't use N+1, what can we do? Got you. This is not an official thing, so don't go tell this to Dr. West and be like, look, formula. It's just a me thing that I made up to make life easier. So instead of N+1, we're going to do N1 plus 1 multiplied by N2 plus 1. And we're just going to say that N1 is the neighbor on the left. And we're going to say N2 is the neighbor. This is complex splitting, exactly. So for complex splitting, you cannot use N+1. This is not something you're going to get in here. textbook. I just made it up because it makes life. Okay. So n1 plus 1 times n2 plus 2. So, what? Okay, sorry. So on the left, how many neighbors do we have? 3. So we're going to say n1 is 3 plus 1 times, and I'm going to do it in red just so you know it's the red hydrogen we're looking at. How many neighbors are on the right? 1. So we're going to say n2 is 1 plus 1. All right, guys, what's 3 plus 1? 4. Absolutely is 7, yes. What is 1 plus 1? 2. Okay. The reason I wrote it out like this, I know that you guys can do like simple math, but the name of this is not just going to be a multiplet or whatever. It's going to have a super fancy dumb name. So I'm going to pause here. We're going to pause and we're going to do the tree diagram and then we're going to go back to the name. Okay. So, and just for pretty purposes, I'm going to put the small number first. Just because you could do it either way, but it just looks better if you put the smaller number first. Said what? Did I confuse anyone? No? Okay, cool. So when we're doing complex splitting, we're always going to start with the larger J value because it will look ugly if you do it the other way around. So we have one green neighbor, right? And the green neighbor has a J value of 10 because I said so. So we're going to say this splits by a value of, that's probably not even, but that's what. A value of 10. So we're done with that side. So now we have to split it 3 times because we have 3 blue hydrogens. But what was the value for the blue hydrogen? 5. Now we're going to split each of these two 3 times by a value of 5. And I'm going to try to not make it ugly, but okay. Okay. So we're going to say proportional, even though it's. So we're going to say this is 5 hertz. And this is 5 hertz. Notice, unlike regular splitting up top, there is no overlap. And the reason there's no overlap is because if you think about it, there's 10 units of space here versus this is only 5 units. So in reality, this is only reaching like 2.5 units, 2.5 units, so they're not going to touch. Yes. We're going to do it 3 times, so we're not done yet. This is only the first one. Now, we're going to do it one more time. So, bam. So now that those are the same J value this time, we do have overlap. So these ones in the middle are going to be thick. All right, and we do this one more time. We get bam, bam. Here to go on, but I didn't mean it like that. That was funny. Okay, so this one is going to be really thick. And this one is going to be really thick. Why is that? Because they overlap. Cool. Same reason. This one's going to be really thick. This one's, wow, that one's really thick. Okay. Ta-da! So we can kind of see how this one's different than the last one. So let's draw what this peak looks like now, right? So we're going to have small peak, a big peak, big peak, small peak, empty space, small peak, big peak, big peak, small peak. Ta-da. That's really not cute, but I hope you guys see what I'm talking about, right? So small because there's no overlap. Overlap means it gets bigger. And then this empty space is just this empty space here. They are attached, so the line goes, but it's flat, right? So what does this kind of look like, almost? Yeah. So as we can see, this is a quartet, and this is a quartet. So back to that funny naming thing, we have double quartets. So we're going to say that we have a doublet of quartets. Exactly, all that stuff. So that's where this kind of naming comes from. So we're going to call this guy a doublet of quartets because sets of quartets. But I told you, yes. So just technically, it's the way it is, right? There, if you said a quartet of doublets, it's not technically right because look at it. But for the purposes of this class, whichever way you do it, that he won't trick you. Like quartet of doublets won't be. Yes. Yes. Okay. So I tried to draw it like right underneath, but it really didn't work. So each of these lines is a peak, right? And usually they're pretty small. But the more overlap you have, the taller the peak is going to be. So this is all one signal, but it's going to have all these little peaks, and we're going to have a small one, a big one, a big one, a small one. Then we're going to have some flat space, and then we're going to repeat the same exact thing because we have a small peak, big peak, small peak, small peak, big peak, big peak, small peak. Over more sense? Okay, cool. So last time I told you you don't ever have to draw this. So how in the world did we figure out this answer without the tree? I read two. Ah, yes. Okay. So we don't do division in this class. Ew. So instead, we do have the number 8, right? And so 8 is telling us how many of these little peaks we have, right? So that's correct. And then as Allison, no, I know it. Because you remind me of a character from Grey's Anatomy. Amelia. Okay, cool. Right? Amelia Shepherd. I mean, you don't look like her. It's just it makes my brain makes the connection. Addison's a whole other character, anyways. Okay, don't watch it. It's not good. But I am obsessed with it. All right. So when we're naming, we're going to use the multiplication sign as of. And then on either side of it, we're just going to name it. So we have a doublet, because it's 2, of quartets. Yes. Yes. And then you. Yeah. So how do you know? Okay, so that's a great question, and I actually had set it up like that, and I just turned it at the last second. So you want the smaller number first, but for the purposes of this class, as long as you get those 2 pieces, you're fine. Because he's not going to ask you like A is doublet of quartets and B is quartet of doublets. So as long as you know quartet and doublet exist, and it's together, you're going to get the right answer. Okay, so you. No, I asked him before too. He was like, I don't care that much. I was like, cool. Yes, Eric. Yes. So basically what you did is these steps a lot faster in your head. Right? So I'm just breaking it down to the absolute smallest pieces. And then I want you guys to be able to practice this until you get to a point, like you said, where you can just look at it and say, okay, one side's a doublet, okay, one side's a quartet. Doublet or quartet. No, yeah, exactly. Because the double bond is indicating different J values. So whenever we have different J values, we do this. Don't do normal splitting across double bonds. Okay, cool. Now that we sort of kind of have an understanding of this, I'm going to confuse you. And I'm sorry. Wait, yes. No. No, trust me, I didn't understand the tree diagram until like the second time I tutored this class. So it wasn't important. But then once I understood it, I was like, oh, that makes sense. Okay. Yeah, I'm just gonna move this back up because. So yes. Any other questions before I confuse you? About which part? I haven't brought it up to anyone yet. I've been thinking of like patenting it. I want students in the future to like be like, yes, the Hertz, whatever. But that Vardanian method, we love whoever that old dead bitch is. She helped us a lot. Okay. For this class now. Okay. So I like Dr. West. He's a great guy. We're pals. I hate when he asks a question that says theoretically because it's stupid. Just ask me actually, right? But he gives it to you. So yes. Yeah, he's gonna ask you pretty much this exact question, wink, wink, nudge, nudge. And it makes me really angry. So I'm gonna give you guys all my rage and help you figure out the answer. So he's saying, theoretically, let's say that JAB does not equal JBC. So we're saying that this value, let me draw the hydrogens actually. So I can tell that my voice got really loud and angry, and now I'm like calming down. So I apologize for that. Wish I could put like a headphone warning watching later. But okay. So A, B, and C. We're saying that J, A, B, so this J value, which I made really wonky for no reason, is not the same as J. Wow, this was too ugly. I'm sorry. Yes, I will definitely do that. This is J, B. I don't know why this computer only like will let me have like half of kind of aggravated, but whatever. All right. So in reality, what is the hybridization of all these carbons? sp3. So in reality, are these J values different? No. So we're just playing pretend. We're playing make believe. And we're going to say that JAB and JBC aren't different because why not? We live on Mars. So for some reason in my handout, I decided not to tell you which one you're looking for, but we're looking to find the multiplicity of hydrogen. Does it say it in there? Oh, okay. Well, no, I know, but we're looking for this one. So I want the answer for HB. He'll say that in there. So he'll say, how many peaks would you see for HB if this? Okay. So HB is the blue one. So we're going to do the fancy rosemary method. Yeah. No, we don't even have to know the J values. We don't care. So compared to hydrogen B, how many neighbors does it have total? 8, exactly. But we have to count them as separate. So how many red neighbors do we have? 6 plus 1. How many green neighbors? 2 plus 1. 7 times 3. Simple math. 21. Someone say 5. Ouch. That hurt my brain. Okay. It's okay. We're not math people here. That's fine. This is a safe space. And then if you, I would, okay, give me the name for that just for fun. Yes, a triplet of septets. And also because we're not too exact here, you could have also said a septet of triplets. And for this exam, that would be equally correct. Yeah. Yes. Yes. And I feel you're confused. The only reason we're doing that is because Dr. West said theoretically they're not the same. Because theoretically we care about this. Right? So if he says theoretically, nothing's going to make sense in that question, but I believe in you anyway. When you get your test, or like it's online, so just get a piece of paper and write theoretically on it, so then you know, like you remember, or don't. I don't know. I don't know what I'm saying. Yes. There's 2 A's. So what's the first thing we look at when we're talking about NMR? Symmetry. I said something that wasn't symmetry, but we're going to ignore that. So if we get rid of all the mess that I drew in here, we could see that this has internal symmetry. So these 2 methyls are equal. So that's why it counts as 6. Yeah. For this kind of question, he will. Yeah. I think you put 2 pieces together, and that's what made you confused. So what we're saying is that we're using 6 instead of 3 because all 6 of these hydrogens are neighbors for the blue. But the reason we're not doing 6 plus 2 plus 1 and doing that simple way is because he said theoretically they're not the same. So yeah. Hit me. Because that's what the question was asking. Never mind. Yeah. Oh, I do say it in the question. Wow, I can't read. Don't be Rosemary. Read the question. Another thing. Don't be Rosemary. Count your carbons. It'll make sense when the time comes. Okay. So I believe I showed you guys the J value stuff. I don't want to rewrite it, so just party over here for a second. All right. These are the J values you have to know. So most likely, wink, wink, nudge, nudge, he's probably just going to draw something, I don't know, like this. Everyone is looking down, so I'm just going to keep circling around. Okay, cool. Around this, something like this. And he's going to say, what's the J value for those 2 hydrogens? And if it happens to be axial, it's 14. If it happens to be equatorial, 5. Axial, equatorial, 4 to 6. Those ones we don't care as much about. You want to know axial, vicinal, which is 7, and geminal, which is 12 to 15. Geminal is just when they're on the same carbon, like so. And something kind of wonky that we have here is W coupling. Truly, I don't know why it happens, but it looks like a W. So if it looks like a W and there's a carbon in between, it's going to be 0 to 2. Someone had a hand up. W, okay, so yeah. This hydrogen is one, hydrogen is the other. Sideways W, yeah. 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 The car plus curve. Hi, look. Take a look at the car plus curve. That's it. I don't know. I've never seen a question directly about the car plus curve. I don't see your exam before you get them, so that's not like law, but I wouldn't spend too much time focusing on. Just know the big things, like what's 0 degrees, what's. I don't know that off the top of my head. Okay. Yes. Don't worry about that yet. That's chapter 14. Yes. Great question. Great question. Okay, so if you remember from Orgo 1, and everyone's like, ooh. So when we have this chair structure, we are going to have one hydrogen that's going straight and one that's crooked, right? So the one that's going straight is axial. The one that's crooked is equatorial. So when we're comparing the straight one and the straight one, that's axial, axial. If we were to compare this one and this one, that would be axial, equatorial. And then if it was two crooked ones, it would be equatorial, equatorial. Very good questions, everybody. Yeah, W coupling is just when there's a carbon in between them. So like it technically doesn't follow the 3 bond lengths rule, and it's like 1, 2, 3. So it's 4 bonds between them. It kind of looks like a W. Two to 4. So the only time in this class you will ever see the not 3 bond lengths rule, it will look exactly like that, and the answer will be 0 and 2. He probably will do axial, axial, but okay. We still technically have 2 minutes, so I want to run through one more thing really, really quick. Okay. 2D NMR. These are super simple. All you have to know about it is like what they're called. So we have cozy here. Cozy, I don't remember what exactly it stands for. That's fine. It's not important. What you have to know about cozy is it's going to tell you more information about adjacent hydrogens. So hydrogens that are next to each other. Since they're next to each other, they're nice and cozy. Yeah, they're like on adjacent carbons. And they're so close and cozy with one another, so that's why cozy is used. It's correlational spectroscopy. Oh, that's it. Okay. Yeah, I think so. That could be. I just could have completely made that up. No, it is correlation spectroscopy. Heck yeah. I remembered something. What? No, I know. Okay. So that's, I'm not gonna get, you can look that up, whatever. What you have to know is this is gonna tell you the difference between a CH3, CH2, CH versus just a C. You can remember this because it's giving you in-depth information. Depth, in-depth. Thank you. All right, het core, just know it stands for hetero nuclear correlation. Okay. And it's just talking about different atoms with different. And technically, it is still 11:50, so I did finish on time. All right. Have a wonderful day. I will see you guys in